Hello everybody, let us start lecture 60 and the course is on phase diagrams in single component and binary systems. And the topic to discuss is on eutectoid as well as peritectic phase diagram. These two phase diagrams we will consider. Till now what we have considered is eutectic, and we have also started discussing on eutectoid, and we have taken regular solution approach. And we also know at what condition these phase diagrams would appear in the system. Okay. Now, with the same, we basically continuing the same discussion on eutectoid, we will try to see whether we can have some more information of the typical phase diagrams observed in material science with the help of eutectoid phase diagram, and also we will try to consider peritectic. Now, you see that we have considered eutectic, eutectoid we will be continuing, and we will also start peritectic. Why we are taking these three phase diagrams? Because there is one important phase diagram in metallurgy as well as material science, that is called iron carbon phase diagram. In fact, our materials around it, all the engineering materials, even 75 to 80% materials are made of steels. So, that is what we will consider, that steel phase diagram, and we will see that steel phase diagram has eutectic, eutectoid as well as peritectic reactions. So, that is what we have considered. We are considering these three type of phase diagrams. Now, continuing our eutectoid phase diagram, in fact, if we see that we are considering binary solution with A and B, these are the two metals, and we are taking X A and X B, these are the two mole fractions of A and B, and when we add them together we are getting 1 mole of solution, right. And for eutectic, and of course, we are taking temperature and pressure constant, and then we are trying to see the free energy composition diagram and see what is the stability of different phases. Pressure is always kept at 1 atmosphere, and remember why we are keeping pressure at 1 atmosphere, because till now what we have done, when we started discussing binary systems, we have actually started discussing on the basis of solid and liquid solutions, and we got eutectic. Now, in case of eutectoid, we have considered solid solutions. Now, those solid as well as liquid solutions can be considered as condensed phases, and on the condensed phase the effect of pressure is minimally felt. Okay. You have to put very high pressure to have a change in their molar volumes, right. That is what and also the ambient condition, which is 1 atmosphere pressure, we do get to see those phase diagrams, fine. That is what we are taking pressure to be 1 atmosphere all the time. Now, from there, when we have taken solid solution and liquid solutions, we got eutectic. Phase diagram, and when we have taken two solid solutions, we have gotten eutectoid phase diagram. So, if I try to draw the eutectoid phase diagram, this is x b equal to 1, this is x b is varying this way, and this is x b equal to 0, and we have a curve like this. Fine. Okay. So, this is typical temperature versus composition, this is gamma, this is S1, this is S1 plus gamma, this is gamma plus S2, this is S2, this is S1 plus S2, and this temperature is this composition is T XE X ET, because eutectoid we have marked it as ET, and this temperature corresponds to T ET, that is eutectoid. Okay. So, this is typical phase diagram of eutectoid. This is typical eutectoid phase diagram. Now, here S1 and S2, why we are putting S1 S2? Because both of them have the same crystal structures, though they have positive heat of mixing. Okay. In case of solid, so that it will be broken into two solids S1 and S2, one will be A rich and one will be B rich, and in order to mark the differences we are putting S1 and S2. So, corresponding free energy composition diagram at any temperature, let us say I am taking this temperature, this is T1, let us say. At T1, what will be the free energy composition diagram? This is G, this is XB, XB equal to 1, XB equal to 0. Now, gamma, let me draw the gamma first. This is gamma, G2 of gamma. Remember why you are putting G2? Because we know that G2 is the solution free energy with G1 plus delta G mix. Fine. So, G1 is the unmixed condition, G2 is the solution, and delta G mix basically gives free energy for mixing when we mix two elements. Now, this is G2 of gamma. Now, let me put G2 of S solid, that would be, I can put it like this, this is G2 of solid, and we can have common tangent. One common tangent will be passing through like this, another common tangent will be passing through like this. So, these are the equilibrium compositions at T equal to T1, and these compositions we can mark XB of solid 1 in equilibrium with gamma. This is XB of gamma in equilibrium with solid 1. This is XB of gamma in equilibrium with S2, and XB of solid 2 in equilibrium with gamma. So, these are the four compositions, and corresponding compositions are, these are the points which will be corresponding compositions, these four compositions. You just take those informations there at that temperature T1. Now, this is one part. The second part is, here also we can see two T naught points. What are those two T naught points? T naught points indicates this is one point, this is one T naught, another one is here. Okay. So, this T naught point, condition for T naught is G2 of gamma equal to G2 of solid. Okay. So, this is the condition we have to follow. So, we see that these 2 points we have, this particular condition is met, and now this composition is lying between two equilibrium composition XB S1 gamma and XB gamma S1. We can put it as X naught of with respect to S1 gamma, and the another point we can put X naught with respect to S2 gamma. Is that correct? So, that is lying in between two equilibrium compositions. So, that means that point would be also can be reflected here. So, these are the 2 points. These are the 2 points. Like that way, if you change the temperature, and as you keep drawing these free energy composition diagrams, you will see you can actually make a dotted line connecting all those T naught points. So, if I do that, you will see that will actually merge with transformation point in the pure conditions. Here also I can do it like this. So, these two dotted lines will merge at one point also, just like a liquid case. Fine. Now, if I try to see right side of it, so let us say I am trying to see right side of this composition, any composition we take on the right side, okay, it will come to this particular, that means let us say I am taking a composition here. Let us say here I am taking a composition. So, of course, it cannot go upward, free energy increase cannot be spontaneous process, but it can go downward. Okay. So, it can go downward. If it goes downward, if it stays within this, let us say I am just redrawing it, let me redraw it. If I take a composition on the right of it, and if that composition falls, okay. So, if a so if the composition is taken to the right of it, so initially let us say I start at a very high temperature. So, let us say I take a composition here. Okay. So, if I start with a very high temperature, the only phase that will be there will be that gamma single phase. Now, of course, when I cool it down to T1, that composition should lie on the gamma 2 of G2 of gamma line. So, it will be, let us say here it is falling. Okay. So, this is the point I am talking about, this is the point I am talking about. So, now that point, only one way it can reduce its free energy, it can come downwards and it will try to reach to the common tangent line, which is the free energy line indicating equilibrium between two phases. So, once, for example, this zone, this left side zone, if I zoom it, I will get a situation like this. Only this part if I do. So, this is the one, and okay. So, common tangent, this one. So, these are the two compositions, XB of S1 equilibrium with XB S1 in equilibrium with gamma, and this was the composition XB gamma on equilibrium with S1. Okay. So, these two compositions, what we have drawn, what we have seen here, that is the one, and this is the T naught point. T naught point at temperature T equal to T1, this is the point I am considering. Okay. Right side of this particular point, any composition if I take, and if I start at a very high temperature where single phase gamma is there, and then I drop it to T1. So, that composition alloy will be lying, the free energy of that composition alloy will be lying on the green line, which is G2 of gamma. So, it will lie here, let us say this is lying here, fine, this is the composition I am taken. So, it cannot go upward, so it has to go downward. Okay. So, if I go downward, I see that it can end up to common tangent. Once it touches common tangent, so that then the composition, that composition will be distributed into let us say this is the composition of X1. So, X1 would distribute into XB of gamma in equilibrium with S1 plus XB of S1 in equilibrium with gamma. So, that means that single alloy we started with X1 composition at T1, it will actually have a long range diffusion and form two phases, which is S1 and gamma of two different compositions. So, this is equilibrium situation. So, we get equilibrium transformation, and here solid to solid transformation is taking place. This is the equilibrium phase transformation. Of course, we can write equilibrium solid phase transformation, but here what I am getting from a single composition to two different compositions. So, then it will be definitely transformation. Fine. Okay. Now, let us consider left to that. If I take any composition left to that, so that composition would again lie on G2 of gamma. So, it will be here, let us say here. Now, if I take this particular one, it cannot go upward. So, it can only go downward to see the free energy decrease. From here it will go and then again it will go down to the common tangent. Okay. So, that means there are two possibilities of decrease in free energy, and we see that from that point left to that T naught composition, we get a situation that composition, same composition can actually reach out to a solid 1 without changing the composition. So, that means if the system finds that there is no more change required, only the crystal structure change, the system would try to follow that, because for that we need a less activation energy. So, this is part of the phase transformation kinetics that needs less activation energy, but and also that phase will be metastable, because the final equilibrium phase is definitely having composition this and this. So, the final it will definitely come back to that particular equilibrium phases, but in between it can actually stay at this location, at this location. So, at this location I could see that this is applicable for composition right to T naught compositions at temperature, at any temperature. Fine. So, if I take a composition, and here T naught is basically for S 1. Okay. So, now composition taken left to T naught S 1. So, then we have possibility of having S 1 with x, let us say x prime. So, this composition, let us take this composition is x prime, x prime. So, x prime, and x prime is actually greater than x b S 1 gamma. So, that means it can actually have a solid solution of S 1 from gamma. It can come actually from gamma to S 1, it can transform with the same composition without having any long range diffusion, only crystal structure will change, and that time that composition is more than the equilibrium composition that can stay in S 1. Okay. So, this particular transformation is actually having negative delta G equal to delta G, let us say 1 is negative, but it can also go to common tangent, where x prime will divide into two composition, x b S 1 gamma plus x b gamma S 1. Okay. So, then again it will break into two compositions, fine, of two phases of two different compositions. So, here we have long range diffusions. Here also if I see the total, and if I try to look at gamma to S 1 plus gamma transformation with x b gamma S 1, and here is x b S 1 gamma, and here the composition is x b prime. Okay. So, I see that this is also partitioning, but this transformation, this particular transformation is actually partitionless, fine. So, and in this case the free energy change G 2 equal to also negative, and we could see that total free energy, if I try to look at from this to this particular place, this free energy if I try to see. So, this one, this is G 2, let us say delta G 2, and this one is delta G 1. Delta G 2 is greater than delta G 1. So, that means driving force for equilibrium partitioning transformation is more, but still it goes to, it tries to attain that solid 1 with excess solute, we can say supersaturated solid solution. supersaturated solute solution, we can get with excess solute of B, fine. That happens since it requires no long range diffusion. So, this is also called, this is also a kind of metastable transformation. This can also be possible. Of course, this one is this part, this partitioning, partitioning is stable transformation, whereas partitionless is metastable transformation. Fine. So, this is also a possibility. In fact, we see an example of partitionless transformation in case of steel. In case of steel, in order to understand that, we will try to see in case of the steel phase diagram, we have an eutectoid phase diagram. There we have to change our policy of regular solution, because here the crystal structures will be different. A and B, those pure metals, here in case of steel we will have to consider iron and carbon, their crystal structures are different. So, that case we have to draw the free energy composition diagram differently, but there actually we do experience such partitionless transformation, and that transformation yields one important phase which is called benite. Okay. And also we get martensite there. Okay. So, that happens due to partitionless transformation with, and there we have in iron we have excess carbon, and that allows that phase to have a much higher hardness than normal, we call it ferrite, the normal ferrite which forms due to partitioning transformation. Okay. So, we will discuss with the help of the free energy composition diagram in case of steel, but you know, just like in case of eutectoid, eutectoid also we do get partitionless and partitioning transformation. Similarly, if we try to go to that side, left to that we have partitionless partitioning, and right to that we have partitionless transformation. Fine. Similar logic you can put, but interestingly one composition range, if I try to look at this composition range, you will see the gamma will be stable. So, the gamma will remain gamma. Okay. There will be no transformation, because below that we do not have any other phases, any other free energies where the phases can have that transformation. Okay. Similarly, in case of eutectic also, in between that two liquid compositions we will always get liquid there. Okay. So, this is one part we wanted to understand. Now, let us try to look at iron carbon system. In case of iron carbon system, let me draw that iron carbon system phase diagram. I am just drawing schematic, you have to see some internet information to check those compositions. I will try to put those compositions as far as I recall. Okay. In case of iron carbon system, we will have iron and Fe3 say diagram. It is also called a metastable diagram. Why metastable diagram? Because in case of iron carbon system, we have, if it is stable, that carbon graphite should have been there, should have been considered, but here we are considering one compound Fe3C. Okay. So, if I try to draw that particular phase diagram, it will look like this. Fine. And this is weight percent of carbon, and on this side 6.67% of carbon we are putting, that carbon corresponds to Fe3C phase. Fe3C phase. Now, on the left side at a high temperature, which is let us say 1539 degrees Celsius, the melting point of pure iron. So, we have, so now here I can have a small section. So, this is the typical diagram you will notice. This temperature is around 14 90 degree Celsius, this is around 1405 degree Celsius, this composition is around this is around 0.16, this point this composition around 0.05 and this is this composition is 0.55, this is 910 degree Celsius, this is 1147 degree Celsius. This is 4.3 weight percent carbon, this is around 2 weight percent carbon, this is 0.8 weight percent carbon and this point is around 0.025 percent carbon. So, this is typical phase diagram we observe and this is liquid. Now, we have three unique reaction, one is this, another one is this, another one is this. And now, let us put the phases. This is delta plus gamma, this zone is delta, this is gamma plus liquid, this is liquid plus Fe3C, here it is gamma, this zone is alpha, alpha plus gamma, this is alpha plus Fe3C and here it is gamma plus Fe3C. So, these are the phases. Now, here we see that one eutectoid reaction, one eutectic reaction, those two are happening. We will talk about this particular reaction which is called peritectic. We will talk about this little later, but since we are talking about that partitioning and partitionless transformation and mainly about partitionless transformation where we get benite or martensite, that means supersaturated iron and supersaturated with carbon, and this is pure iron side. And remember, alpha is called ferrite, gamma this is alpha, gamma is called austenite, gamma, and delta is this is delta iron, this is called delta iron, and its crystal structure is BCC, body centered cubic. This crystal structure is also BCC and this is crystal structure is FCC, face centered cubic. Now, Fe3C is a compound. Now, if I try to see the eutectic one, if you see this, let us say this, there are 3 points, let us say this is A, this is B and this is C. Instead of C, I can mark it as let us say this point is let us say M, this is N, this is let us say P. So, we have also missed one particular zone, this zone would be delta plus liquid. Now, if I try to take if I mark this point as M, this point is N and this point as P. So, the M is nothing but eutectoid point where gamma changes to alpha plus Fe3C. So, two solids are forming and these are having different crystal structure. So, this is so this is having complex crystal structure. This is FCC, this is BCC and this one is orthorhombic. This is orthorhombic crystal structure. So, that means you see that gamma it converts to two solids of two different crystal structures. Now, in the previous case when we talked about gamma takes to S1 plus S2, that is also eutectoid reaction, this is eutectoid reaction. This is also eutectoid reaction And this reaction, the only difference between these two eutectoid reaction is, in this case this crystal structure was same. S1 and S2, that is what we had, a continuous line like this. When we tried to draw free energy G versus XB, the plot was like this was S. So, this zone is S1, this zone is S2, but in this case we had two different crystal structures are forming from another phase. So, this eutectoid, when we have this kind of situation, we cannot draw the free energy of alpha and Fe3C combinedly. They will be different plots for both the phase alpha and Fe3C. Okay. So, then correspondingly there will be change in the way we have considered equilibrium. Now, let us look at that equilibrium part, considering free energy composition diagram. So, if I try to draw free energy composition diagram in order to show eutectoid positions. So, this is x b equal to 1, x b equal to 0. Now, if I try to draw at this temperature, let us say I am trying to draw at this temperature, let us say here, this is the temperature I am drawing, T1, let us say T equal to T1, fine. So, here the gamma phase will have a continuous line, okay, or gamma phase I can draw it with green color. This is the gamma 1. Now, alpha will have a plot here, this is alpha, G2, or we can say G2 alpha, and this one is G2 gamma, and this axis is G. And now, let us try to see what happens to Fe3C. Fe3C, if I take it as a kind of near stoichiometric compound, so that case the composition does not vary, it could be considered as a single line for the Fe3C for free energy composition. That free energy composition diagram for Fe3C can be considered as a single line. Why? Because if we take perfectly stoichiometric compound, but since perfect stoichiometry is not possible, so there will be always little width in the free energy composition diagram for Fe3C. So, the Fe3C, here you have to make a change, this XB, in this case XB we cannot consider XB, rather we can consider this is pure Fe side, percentage of carbon, and here 6.67% carbon you consider, because Fe3C has a composition 6.63% carbon, weight percent carbon. So, now at this situation the Fe3C will be a kind of a very narrow free energy line we can consider. So, Fe3C, if I try to draw it with a different color, so if I do this, so Fe3C would have a plot like this, G2 Fe3C, and Fe3C is also called cementite. Fine. Now, if I draw a common tangent, so one common tangent can be reflected, this is one common tangent, another common tangent is here, fine, these two common tangents, and this composition is here, okay, and this composition is here, and this one is here, and this one is at this location. So, I have just made little adjustment in order to show the differences, but here also you can actually mark them. This one is X with carbon of alpha in equilibrium with gamma. This composition is Xc of gamma in equilibrium with alpha. This one is x b x or we can put it like this. This one is xc of gamma in equilibrium with, I can put Cm, this cementite I can put Cm, x gamma, that gamma composition in equilibrium with Cm, and this particular composition I can write it as, this is Xc in equilibrium with gamma, okay, the carbon concentration, fine. So, these 4 compositions we have marked there at T equal to T1. Now, let us see whether we get T naught here. We do get a T naught here. So, the T naught would be here. So, if T naught would be here. So, if I draw that T naught will be lying, this is T naught, I can put it as T naught gamma, okay, T naught alpha gamma or alpha with respect to that solid which is in equilibrium with gamma. Okay. So, this T naught gamma, T naught alpha is actually lying at this location, fine, this is the location. Now, if I, and this is my composition, let me mark those composition. This is x c of alpha in equilibrium with gamma, this is x c gamma in equilibrium with alpha, this is x c of gamma in equilibrium with Cm, this is x c Cm in equilibrium with gamma. These are the 4 compositions we have marked there, same way we have done it there also in the phase diagram, iron carbon phase diagram. Now, if I take left to this composition, what will be the situation? Right to the composition, definitely it has to go to an equilibrium transformation from solid to 2 different solids, but on the left to the T naught we will have a typical situation. Now, let us look at that part. If I zoom it, this is x c or weight percent of, instead of percentage of C, these are actually this x is, you can remember this x is nothing but not mole fraction, it is a weight fraction, this is weight fraction. Please consider that this x what we are doing here, these are weight fraction, weight percentage, there is only change, x is not mole fraction here. Okay. If I do that, so this is G2 alpha, this is G2 gamma. Now, we have a common tangent. This is the composition which is nothing but Xc gamma in equilibrium with alpha, and this is the composition Xc of alpha in equilibrium with gamma. Now, this is the T naught point, fine, this is G axis, and now if I take a composition left to this, and if I start at a very high temperature single phase gamma zone, and that gamma is taken to temperature T1, okay, this is also T equal to T1, at that condition left to that, the initially to start with that alloy composition, iron carbon alloy composition will lie on G2 gamma line. Okay. So, this will be lying here, let us say I am taking a composition. So, that means it can go down, here it can go down, it can further go down to this common tangent, okay, as we have discussed before. So, the alpha, the saturation carbon content is equal to x c alpha gamma. Now, we are getting gamma to alpha if I mark those points, let us say E, F, G. Okay. So, gamma to alpha we need to have a change from E to F. So, delta G is negative. So, this does not require composition change. It is not required. Okay. So, that means this is partitionless transformation. Fine. It can still go down because this is actually a metastable supersaturated ferrite or alpha, okay, or solid solution. Fine. It can actually further go down, that means it F to G it can go. So, then we will get gamma of composition, let us say this composition is taken to be x naught, it first goes to alpha of x naught, then again it will go to alpha of x c alpha gamma plus gamma x c gamma alpha. This is the transformation pattern we will have. So, in this case we will get x alpha, initially it was alpha. So, alpha x naught it goes to alpha. So, basically from here it goes there. Okay. So, like that two stage transformations can be possible. Now, here we are getting the same BCC phase, but it contains more carbon when it reaches to a F E to F, more carbon than the equilibrium carbon content is in ferrite. In fact, this particular supersaturated solid solution of ferrite, it can have a transformation like bainite or martensite. Okay. So, this transformation is possible due to partitionless transformation. Of course, this one is partitioning, but it is a second stage. First stage is the partitionless, and it is a quite possibility. Why? Because it does not require long range diffusion, because in case of partitioning we have a long range diffusion, that is what it takes time. But for this bainite and martensite transformation, if you do not allow that time for the diffusion of carbon, then definitely the supersaturated solid solution of alpha is quite possibility. Fine. So, that is what I wanted to bring in, this difference in crystal structures. Accordingly, the free energy composition diagram is shown in this particular G versus composition plot. Now, if I take the composition on the right, definitely the similar situation. Let us say I am taking a composition here on the right side, it can only go to a partitioning transformation. So, this one can only have partitioning transformation. Fine. Okay. As usual, but if I try to, for example, the common tangent, another common tangent with Fe3C was here. So, if I take a composition at this point, definitely the gamma will be stable phase, it cannot go for any transformation. Okay. So, this is one example in case of iron carbon system. So, iron carbon system, if you look at, we have eutectic, this is eutectic, this is eutectoid, fine, and here eutectic in case of iron carbon system, eutectic can be placed like this. In case of iron carbon system, eutectic is nothing but liquid goes to equilibrium transformation, it is going to gamma plus Fe3C. So, this is eutectic transformation in case of iron carbon system, fine. And both the cases we have considered Fe3C, And actually Fe3C, if you hold it for a longer duration, it can convert to iron plus carbon, and this carbon is in the form of graphite. Okay. In case of cast iron, we do see such kind of situation where we have alpha plus graphite, and this particular thing can have different morphology. We can have different cast irons. Okay. So, these cast irons could be grey cast iron, spheroidal graphite cast iron, or malleable cast iron. But of course, when I have this, that time that will be called as white cast iron. Okay. So, this is on the part of cast iron, and the carbon content is pretty high, which is 4.3% carbon. And eutectoid we have seen just now, and eutectoid part till 2% carbon. Okay. So, if I see this phase diagram again, till 2% carbon up to this, we consider that is to be steel part, and that beyond 2% of carbon we consider it to be a cast iron part. But below 2% carbon we have a eutectoid reaction or eutectoid point, where we get alpha and Fe3C. But there is one more point which is lying little at a higher temperature, where we see that this is the point I am talking about, this is the point which talks about a transformation which is, so another transformation we are getting, where we are getting delta plus liquid, it actually going to gamma. Okay. So, this is this particular equilibrium reaction called, this is eutectic reaction, and this is called peritectic reaction. So, this peritectic reaction also you see, this is BCC and this is FCC. Okay. So, here also we have to see that how the free energy composition diagram would look like to get the phase diagram around that peritectic point. In case of peritectic point, the transformation is looking like this. If I only draw the peritectic part, this. So, this is the peritectic point, and this is delta plus liquid, this is gamma, this is delta plus gamma, this is gamma plus liquid. So, now around this, this is, let us say this is composition, this is percentage of weight percent of carbon, and this is temperature. Okay. So, in the next class we will try to see how the phase diagram phase diagram can have a relation with the free energy composition diagram, okay, in case of peritectic. Fine. So, till then let me close today's discussion. We will continue further, though you are seeing that we are extending our discussion little more, and we have reached to 60, but we will continue for another 1 or 2 lectures, and then we will conclude. Okay. So, let me stop here. Thank you very much.